So let's consider this term s squared, which equals x0 squared minus x1 squared. x0 is c times t. So we can say that s squared equals c squared t squared minus x1 squared. Dividing through by c squared t squared, we get s squared equals c squared t squared into 1 minus x squared over c squared t squared. Or s equals, taking the square root, s equals ct into the square root of 1 minus v squared over c squared. V squared because that is x squared over t squared. Now divide both sides by c. S divided by c is t times the square root of 1 minus v squared over c squared. And that we call tau. And that is what is called the proper time. It is the time which is invariant. Since s squared is invariant, then s divided by c must also be invariant, because c is a constant term. Tau, the proper time, turns out to be the time which is recorded on the clock with which you are travelling. You'll remember that if you are travelling, everybody else's clock appears to be running slow. The only clock which appears to be keeping proper time is the clock that you have with you in your frame of reference. And that we call tau, the proper time. And it is an invariant quantity which everyone in the universe can calculate. We spoke of x as being a 4 vector. We're now going to create another vector which I'm going to call the 4 momentum vector, and you'll see why in a moment. Let's call it capital P. And I'm going to define it as m, which is mass, times x0 divided by tau, x1 divided by tau, and so on, x2 divided by tau and x3 divided by tau. But to keep things simple, we're just going to do it in the time dimension and one space dimension. Remember, x0 is c times t. So the first element of this vector, which we shall call p0, is m and then ct divided by tau. The second element is m x1 divided by tau, which is the same as mx1 divided by t times t over tau. But we've already shown that t divided by tau is 1 divided by the square root of 1 minus v squared c squared. And so we can conclude that the first element of this 4 momentum vector term, p0, equals mc divided by the square root of 1 minus v squared over c squared. The second element, p1, equals mv divided by the square root of 1 minus v squared over c squared, because x over t equals v. Now, we can use a famous expansion in mathematics, which reads like this. If you have a term 1 plus x all to the power n, then you can roughly write that out as 1 plus nx plus a lot of other terms that we can forget because they will generally be small. If you use that expansion for 1 minus v squared over c squared to the minus 1/2, that can be written as 1 plus v squared divided by 2c squared. And that means that p1, the second term of our 4 momentum vector, becomes mv plus mv cubed divided by 2c squared. And what is mv? Well, we recognise that is ordinary momentum. So what is mv cubed over 2c squared? Well, it must be some kind of relativistic correction when speeds approach the speed of light. But you can see that if v is small compared to c, then that second term just falls away and we get the standard momentum term, p1 equals mv. And so we can conclude that p1 must be a momentum term. What about p0, the first term of the form momentum vector? Well, that is mc divided by the square root of 1 minus v squared over c squared, which using the expansion is mc plus 1 over 2c times mv squared, plus a lot of other terms we can ignore. If you multiply both sides by c, we get that cp0 equals mc squared plus a half mv squared plus some other terms. We recognise half mv squared, that's a kinetic energy term. So cp0 must be an energy term. But what's this mc squared? Well, mc squared must be the energy you have even when you don't have any kinetic energy. It might be referred to as the rest mass energy. And that is the famous equation E equals mc squared. So let's look at this 4 momentum vector and see if we can find another invariant quantity. With the other 4 vector, we found that x0 squared minus x1 squared was invariant. Let's consider for the 4 momentum vector p0 squared minus p1 squared. Well, that's simply going to be mc gamma squared minus mv gamma squared, and that is m squared gamma squared into c squared minus v squared, which is m squared gamma squared c squared into 1 minus v squared over c squared. But 1 minus v squared over c squared is simply 1 over gamma, so that becomes m squared c squared. And so we find that since the mass, the rest mass, is constant and c is a constant, that p0 squared minus p1 squared is another invariant term. It doesn't change. Everybody can count the same. But let's look at this in more detail. What is p0 squared minus p1 squared? Well, p0 squared is energy divided by c. It's all squared. And p1 squared is momentum, little p squared. And that equals m squared c squared, because we just calculated that. Multiplying through by c squared, you find that e squared equals c squared p squared plus m squared c to the 4th, which is the general term for calculating energy when you have momentum. If momentum is 0, if the object is not moving, p is 0, and this reduces to e squared equals m squared c to the 4th, or the famous equation by square rooting both sides, E equals mc squared.